Hi there, this is Physically Attractive, and in this channel I will be sharing my take on the subjects that I'm currently studying as part of my physics degree. Generally, I always try to develop an intuitive understanding of the concepts that I'm studying, explore how everything connects, and try to see the bigger picture. By sharing this, I hope I can help a few people out there who are also struggling or just interested in the topic. So this first video kicks off a series on atomic and molecular physics, as I'm currently studying for that exam. We'll take a look at a very condensed story of the atom and the discovery of its physics. I hope this will provide some context, motivation, and sort of set the scene for the rest of the series. So let's dive into it. Our story begins 500 BC with Empedocles, a Greek philosopher who, among others, proposed that everything in the universe is made up of 4 fundamental elements: fire, water, air, and earth. And while we all know that this idea doesn't really align with modern physics, it does represent one of the first systematic attempts to explain the nature of the material world. Jumping to 400 BC, we have Leucippus and his student Democritus, who took a huge step into the right direction by introducing the idea that all matter is made up of infinitely small, indivisible particles, which they called atoms. They also theorized that atoms were separated by empty space and varied in shape and size, and that those variations gave rise to the diverse materials that we see. Of course, this does have some faults, but I do believe it's impressively to the point, considering that they had no experimental tools available, and also considering how long it took to prove some of those ideas later on. We then also have Plato, who sort of went back to the theory of elements that we had in the beginning and linked specific geometric shapes to those 4 elements, as you can see here. And though this could be considered a step backwards, for me it does demonstrate that the knowledge that we deem obvious nowadays was once hard fought. And when you sit in uni or school and they teach you all those things and everything eventually makes sense, and it feels like this is the only right explanation, they're just feeding you the right answer already, because we know nowadays. But when you're trying to come up with new things, it's much harder. And sometimes you just have to take a guess. That's just part of the process. We don't have to feel stupid when we come up with stuff that maybe doesn't work out. Just a little motivational speech, because we all need one every now and then. Moving on, so it seems like we were already on the right track when things kind of slow down a bit. We have Aristotle, who did have a huge influence on science, but did not support this specific idea of the atomic idea, as he did not believe in the empty space between atoms. He rather promoted the idea of a continuous, infinitely divisible substance that he called ether, and this would fill space. We also, in later centuries, have the Christian Church, who initially resisted the atomic theory, viewing it as incompatible with the belief in the divine creation. But there's one significant contribution that I do want to mention, and that comes from Epicurus, who suggested that atoms have weight and that this influences how they interact and combine. So now we have a period where no significant developments are made regarding the atomic theory. But in the 1700s, things are starting to gain momentum again. Chemists now have some basic experimental tools. They did basically weigh the ingredients and the products of chemical reactions. And we have Joseph Proust, who observed that chemical substances always combine in fixed proportions. I'm going to give an example because it was hard for me to understand, because we take it for granted. If you have 8 grams of oxygen and 1 gram of hydrogen, you will always make 9 grams of water. And it doesn't matter if you have a little bit more oxygen, because you do not have more hydrogen. So here we have a ratio of 8 to 1, and this ratio will always stay the same when making water. And this doesn't directly prove the atomic idea, but it is definitely aligned with it. It also suggested that atoms of the same element are identical in their mass and their properties. And then we also have Antoine Lavoisier, who famously stated, "Nothing is lost, nothing is created, everything is transformed," referring to the mass of the substances, but it did remind me a lot of the law of the conservation of energy that we have nowadays. So it's interesting to see that it already comes up here in the 18th century. But it was not until John Dalton in the early 1800s that the concept of the atom gained widespread acceptance. He provided more experimental support and extended Proust's findings. His law describes that two elements can combine to form different compounds in simple whole number ratios. So what does that mean? Let's say we have nitrogen and oxygen. Those two elements can actually combine to 5 different nitrogen oxides, and it's always dependent on the ratio between the nitrogen and the oxygen. Now, what Dalton found is that this ratio is always in whole numbers. So let's say 1 to 2, 2 to 3, and so on. And this suggested that matter is composed of discrete particles rather than being continuous. We then also have a whole group of gentlemen who developed the kinetic theory of gases, linking properties such as pressure and temperature to the kinetic energy of gas particles. This theory demonstrated what Leucippus and Democritus had speculated centuries earlier, that the macroscopic properties of materials, in this case temperature and pressure, are determined by the microscopic characteristics of the atoms that they are made of. So in this case, the kinetic energy of the atoms. So I think this demonstrated how impressively to the point Leucippus and Democritus were all those years ago. So now things start to develop much quicker. Within only a decade, we go through 3 atomic models. In 1911, we have Ernest Rutherford, who conducted his famous gold foil experiment, which I'm sure most of you know from school, which gave us the idea of positively charged nuclei surrounded by negatively charged electrons. And only 2 years later, we have Niels Bohr, who introduced the energy quantized orbits for electrons based on Planck's quantum theory. But this still didn't quite match our observations, especially the fine structure of spectral lines when observing atoms. And this is why Arnold Sommerfeld refined Bohr's model even further by incorporating elliptical orbits and the quantization of angular momentum. Now, in the 1920s, we really see quantum mechanics taking off. And in 1922, we see Stern-Gerlach demonstrating the quantization of angular momentum in their experiment. And also 1 year later in Compton's scattering experiment that revealed the particle-like behavior of light, which we describe in something called photons. And then 1924, we have a very, very important idea from Louis de Broglie, who proposed that in turn to what Compton discovered, that matter could have light-like properties, which was confirmed only 3 years later in an experiment by Gamma and Davison, who discovered it by coincidence while investigating electron reflection. Now, in between, Erwin Schrödinger took the idea from de Broglie and mushed it together with the classical wave mechanics that already existed to propose his famous Schrödinger equation. And then only 1 year later, we get the uncertainty principle from Werner Heisenberg. And then also 1 year later, a relativistic view on quantum mechanics from Paul Dirac. And all of this only in 1 century. So, in conclusion, the atom had many more surprises for us in store than we could have ever imagined, and there are many more to come. But do we finally know enough to take a glance, or is it even possible to see atoms? Well, the answer is yes. So now in the 1930s, we took that idea that de Broglie brought up to solve the limits of traditional light microscopes that are bound to visible light, which has much longer wavelength than the diameter of an atom, which means that it's impossible to depict atoms with visible light. But now that we think we know that even matter, such as electrons, can have wave-like properties, we can use that to develop something called the transmission electron microscope. So it basically works the same way as the microscopes you used in biology classes in school, just that now instead of a light source, we have an electron source. Instead of optical lenses, we have electromagnetic fields that are directing the electron beam. And we have still a thinly sliced probe that we shine through with the electron beam, and depending on different absorption effects, we can depict the inner structure of that probe. Now, the TEM did not have atomic resolution yet, but we're getting there. One more instrument that I want to mention is the scanning electron microscope, which worked pretty much the same way as the TEM. However, now we're not looking at the electrons that are going through the probe, but rather the ones that are backscattered, or even some of the electrons that are emitted from the probe, which means that we can much better look at the surface of a probe, and we don't actually have to cut it in thin slices. And then with the field emission microscope and the field ion microscope, we finally have the first instruments that can actually reach atomic resolution, where we have a very sharp tip that we apply very high electric fields to, and we then have either the emission of electrons or ions that are then sort of depicted onto a screen. So they visualize the arrangement of atoms on a material's surface in much higher resolution. However, those two had many limitations, and in 1981, we first have a working scanning tunneling microscope, which relies on the quantum effect of quantum tunneling, where we again have a very sharp tip, which is now scanning over a conducting surface. And we're measuring the tunneling current, which gives us a much higher resolution than even the FIM or the FEM, and actually sort of kicks off nanotechnology, because we can now manipulate single atoms. We can pick them up with that tip and move them around. In the description, I will attach a video from IBM where we have sort of a short movie where the actors are atoms. And then one more honorable mention is the atomic force microscope in 1986, which instead of measuring the tunneling current, measures atomic forces, which gives us the advantage that we are no longer reliant on conducting materials. So here we are, from philosophy to physics to actually seeing atoms. We have learned a lot, but mostly we have learned that there is still a lot to discover. And in the next video, we're gonna kickstart a recap of quantum mechanics that we're gonna need to then move on to understand the mechanics of the hydrogen atom, many electron systems, and finally molecules. So stay tuned and hit the subscribe button.